Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of Cheat Cloud. And today we will be talking about modulating heat pumps and geothermal design. Now I'm really happy to make this video because we're going to share some interesting research we've done together with Alpha Innotech, and that will actually be presented at the Geothermal Conference in Frankfurt the day this video is released. So let's jump right into it. Now, when we're talking about heat pumps, they exist in all sorts and forms. But for this video, what is important is the difference between an on-off heat pump and modulating heat pumps. Now, an on-off heat pump is exactly what it says. It is either on or off, meaning that whenever your building demands even a slight amount of heating, it jumps on at 100% of the capacity, and when it is delivered the heat, it shuts down. So it's quite an on-off behavior. Whereas modulating heat pumps, they can function somewhere between 30% and 100% of their full capacity. Meaning that when our building demands just a little bit of energy, it starts at 50% or 60%. Meaning that since it can work at a lower power, it can run more constantly, giving it more running hours. This also means that the wear on these modulating heat pumps is lower than these on-off heat pumps, which cycle constantly between on and off. It also means that modulating heat pumps have a more stable temperature because it can follow the heating demand of the building. It can slow down or it can speed up. Whereas our on-off heat pumps, they jump on, they deliver the heat, and they shut down. And you typically have to work with buffer vessels in order to store some of the heat to flatten out the load to the building. And this also means that since our modulating heat pumps, they can work at a lower capacity, they typically have a better efficiency than our on-off heat pumps. Because you have to imagine a heat pump, all the components, the compressor, the heat exchangers, etc. are designed at full capacity, but when your heat pump is only working at 60% of that, all your components, your heat exchangers, etc. are initially too big. So they are oversized, meaning they can work slightly better. So that's an important distinction, and typically the industry is moving more and more towards modulating heat pumps due to all the advantages it has. Now, for the story of today, we really need to understand the heat pump efficiency. And this is typically measured in one of two ways. We have on the one hand the COP, and on the other hand the SCOP. Now the COP stands for coefficient of performance, and it is the amount of heat a heat pump can deliver per unit electricity. And it's an instantaneous efficiency. So at this instant, what is the COP of the heat pump given our supply temperature to the building, given the temperature from the ground, and given our specific part load in the case of a modulating heat pump. So it's one specific value which varies over time, of course, due to the fact that the temperature evolves, etc. And that's what we call SCOP, the seasonal coefficient of performance, and it's sort of an average value over a season. It's not a specific moment in time, but it's on average taking into account the fact that our ground temperature evolves, our building needs evolve, we have certain part loads. Taking all this into account with a standard predefined calculation method, we can come up with an average efficiency of our heat pump. And typically, this SCOP is higher than our single valued COP because we take into account the fact that, let's say in winter, at the lowest point our efficiency is lower, but on average it's better. So that's why our SCOP is also typically used to compare the efficiency of different systems. Now, why is it important? Well, if we take a step back to what we always talk about on this channel, which is borefield design, we typically start with the building load, the heating and cooling demand of the building, And this needs to be converted one way or another to the extraction and injection load for the ground, for the borefields, because that in the end determines our sizing and our temperature evolution. And typically this conversion between building load and ground load is done by using an SCOP value, which is officially in the technical documentation at B0, W35, or a ground temperature of 0 with a building temperature of 55 degrees Celsius. And that's how it has been going for ages. But there is a problem with this assumption, or there are several problems. And one is that our peak power, so the maximum power our heat pump can deliver, it's overestimated. Because, as we said before, when we're working at a specific peak power, specific temperatures, we are working with a COP, one instantaneous, 1 point of performance. And this COP, at a certain temperature, is always lower than the average efficiency, the SCOP, at this temperature. So because we're overestimating the efficiency of our heat pump at this critical peak power, we're also overestimating the amount of heat it extracts from the ground. So we're overestimating the peak powers on our borefield, leading to bigger systems. But on the other hand, the official documentation always says B0, a ground temperature of 0. But typically when you make a design, if your system even reaches 0, it's in the long run. It's not an average. Not in the mid-seasons, not in the first year. So typically your temperatures are higher, meaning that your heat pump is also more efficient. So when our heat pump is typically more efficient than what is officially in the documentation, it extracts more heat from the ground than what we expect, meaning we have a bigger imbalance, meaning that we should increase our borefield size to cope with this imbalance, as we discussed 2 weeks ago. So that's the counter argument. We underestimate the imbalance. But what is really strange is that our efficiency of our system, it does not depend on our design. If we drill deeper or shallower or denser or use single instead of W tubes, it does not change our efficiency because it's an input. And when you think about it, it should be an output, right? It depends on how you design borefields. So in the research we did together with Alpha Innotech, we said, okay, let's look at 3 different assumptions. Let's design borefields using a constant SCOP like it's always done in GHG tool, but also in EED, for example. Let's take into account the temperature dependency of the heat pump, and because when the ground temperature changes, also the efficiency of the heat pump changes. But then what's most important when we're talking about modulating heat pumps is let us also investigate what the temperature, yes, but also the part load dependency of the COP has to do with our borefield design. And this is really something new because it's not in technical documentation somewhere. Yeah, temperature curves, we know the efficiency of the heat pump for different ground temperatures, but not at different part loads. So this was really something new in the literature. And what we did is we investigated how the required borehole depth should change when we use one of these 3 assumptions, and taking into account the overestimation of the peak power, the underestimation of the imbalance. What effect does it have on the final required borehole depth? But also, what's now the difference in SCOP when we simulate our system? Does this really matter, this assumption? And this is set together with Alpha Innotech, and we presented the results at the Geothermal Congress in Frankfurt later this week. So let's start with the beginning. When we design 3 different buildings, a residential and office building and a multi-utility building, with these 3 assumptions, and we did this for 2 different temperatures to see the effect it has on the temperature dependency. And what we see is that our required depths are more or less the same, actually. And in an office building, it's slightly better when we're using temperature and part load dependency, because yeah, we have quite a lot of cooling and temperatures are rather high, so our heat pump is way more efficient. In the case of the multi-utility building, it was slightly bigger, but it was a maximum of 3% increase in borefield size. So what we can say is that our two problems we saw, the peak power and the imbalance, they cancelled out more or less, which is really interesting. So when we change the assumption, it does not so much change our design in the end. What does change, however, is our average SCOP. So our blue lines are the ones where we use the official B0W35 efficiency. And what you can see is that for the ones with a higher minimum temperature, we see that a temperature dependency makes it such that our efficiency is slightly better. But what is significant is that when we take into account our part loads, we can have an increase of 10 to 15% of a better efficiency. So with the same design, when we simulate it the correct way, we can say, okay, our efficiency is not 4.86, but it's 7 on average. And this is really interesting. And if we, for example, take a closer look at some of the figures for the multi-utility building, and we simulated this at an hourly temperature profile, where you see that there is quite a lot of fluctuation, like we know with hourly simulations. And if you have not seen our video on the importance of hourly resolution, it's linked in the description. But what is interesting, if we then zoom in on the first 5 months and take a look at the COP, the instantaneous COP for every hour, we see that, our temperature dependency, it changes. And because, of course, our temperature also fluctuates, and it's between, let's say, 5 and 5.5. So it fluctuates. But when we also take into account power load, it fluctuates way more. Because in the evening, there might be some demand, but not much. So we are in a very high part load region where our efficiency is really, really good. So this is interesting, because when we're working at peak power, and these are the lowest efficiencies, here we see that our two lines, they coincide. Because at 100%, they have the same efficiency. But on average, taking into account the part load, you see that the efficiency is way more fluctuating, but also way higher for the system in which we take into account the part load dependency. And this you can also see in the following graph, where we had our constant SCOP. And then we see our two lines, which include temperature dependency, and it starts off high and it goes down. Because we have an imbalance. So year after year, the temperature goes down a little bit. So the efficiency also goes down. And you can see that our temperature dependency, it goes even below the average as COP B0. And the reason for that, although it might sound counterintuitive, is because when we're working with this temperature dependent COP, we always assume the heat pump is at 100%. We only take into account temperature dependency. And when we're going closer towards the minimum temperature of 0 degrees, this means that we're underestimating the efficiency, because there is some part loads, but it's not taken into account when we just look at temperature dependency. So there, in the long run, our SCOP value is actually better. But when we use also our part load dependency, we can see that our efficiency is, over the whole 20 years, way better, because we take explicitly into account this part load behavior. And we also have efficiency ranging here from 6 to, 5.4, which is significantly higher than our officially documented SCOP. So why should you care about this research? Well, the thing is, when you design with this variable COP, taking into account the part load, you can have way more advanced simulations, because you can really see the effect your design has on the efficiency. And drilling deeper, drilling shallower, it will all influence the temperature behavior of your system and hence also your efficiency. You can also see the real benefits between using a machine that can work with part load, a modulating heat pump, versus a on-off heat pump, which works at full load. You can clearly see the real efficiency benefits it has to go for modulating heat pumps. But you can also estimate the effect of heat pump oversizing. Imagine you have a heat pump or a heating demand of 8 kilowatts and you install a heat pump of, let's say, 6, which is slightly too low. So it will always, or more of the time, work at a maximum power, which will give you a lower efficiency at 100% peak power or full load. Versus if you say, okay, let's use a machine of 10 kilowatts, that's modulating, then you will see that it will move way more in this modulation degree, where it will work in part load, where it will have a higher efficiency. So these are all things you can now take into account with this research. And perhaps the most important thing for the sector as a whole is that we can show the real efficiency of a ground source heat pump. Because on paper, as we discussed in another video as well, linked in the description, is that the efficiency on paper between a ground source heat pump and an air source heat pump, it's becoming really close. It's the same thermodynamic cycle, so the efficiency becomes also close to one another. But when we take this into account for a geothermal design, we can actually show that no, it's not 4.8, it's actually 5 or 6, or in the case of the office, even 7. So it really changes the way you look at the total cost of ownership of your geothermal system, for example, and it can increase the market share for these type of solutions. So this was kind of a sneak peek. Yeah? It's really new research, and we want to implement this, are we going to implement this in Q1 2026? So stay tuned for that. We're working together with heat pump manufacturers to get the right data to implement it so that you can actually see what the difference is when you're designing with modulating heat pump versus on-off versus using constant SCOP, and you will experience flexibility in the design of borefields that you've never seen before. So I'm really excited to keep working on this, keep working with manufacturers, with you, our users, because you demanded actually this, having the option to work with modulating heat pumps. Stay tuned for that. Share it with your friends, family, colleagues. I hope to see you in Frankfurt, but otherwise, in case you cannot make it this close, we see each other in the next video. Take care.